Welcome to Out of the Lab, a podcast interviewing entrepreneurs who've taken research out of the lab and built it into a company that's serving the world. These entrepreneurs are heroes, and the planet needs more of them. So tune in, learn from their successes and failures, and get inspired. Visit bountiful.work to join our community and realize your power to save the world. Hello and welcome to Out of the Lab. I'm your host, Max Finder. Today's guest is Professor Donald Sadoway. He's a professor of material science and engineering at MIT. He's the author of over 180 scientific papers and an inventor on 35 U.S. patents. Most of his research is directed towards batteries for grid-scale storage and environmentally sound metals extraction technologies. A few of his inventions have become spinout companies invested by Bill Gates, for instance, and other major environmental investors. He's founded 4 companies, and one of them is called Ambri. It's grid-scale energy storage. Boston Metal is a more environmentally friendly way to manufacture metals. Avanti Battery is his new startup, and his first year chemistry course is actually available on MIT Open Courseware, and it's one of the most viewed chemistry courses. There's 35 lectures or something like that. That's how Bill Gates originally found Professor Sadoway. He was watching his chemistry lectures. It was it's the most popular freshman course, I think, at MIT. And they recorded it because there were so many people that wanted to attend it that they needed to put it on video and screen it in overflow rooms. And so that's how Bill Gates ended up having access to this course and meeting him and funding the company. It's a really cool story. Professor Sadoway gave a TED talk that's been viewed like 3 million times or something like that. A lot of it's about the grid-scale energy storage liquid metal battery that he invented, but at the same time it's talking about how he invents inventors, so how he mentors young grad students and postdocs. A lot of these people have gone on to be involved in his companies, either as CTO or in other executive roles. He's extremely impressive, and he's inventing the solutions to global problems. I learned a lot about thinking from first principles, knowing your limitations, asking the right questions, thinking about environmental impact and materials that you might use. He has a really famous expression that if you want to make something as cheap as dirt, then use dirt. I'm paraphrasing. He says it even better in the episode. And in 2012, he was named by Time Magazine as one of the 100 most influential people in the world. He's super impressive, a ton of knowledge, generating a ton of value for our society, mentoring tons and tons of people that are going to go on to be scientific and entrepreneurial and business leaders of the future. And so it was really just a pleasure to speak with him. Enjoy the episode. I learned a ton, and I'm sure you will too. Visit bountiful.work to join our community and sign up for early access to our platform. And thank you. Enjoy the episode. Here it is. Professor, thank you for joining us.
My pleasure.
So I want to start by asking you a little bit about what you've said, how there are no more corporate labs. I mean, 50 years ago, there was Bell Labs and all of these corporate labs that invested so much money in R&D. That's gone away. And so you've said over and over again, the future of R&D is from universities. Can you speak a little bit about that and the potential that universities have for inventing our future?
Yeah, so, if you think back, 50, 75 years ago, companies like GE had massive labs out in Schenectady. All the big metals companies, US Steel, Inland Steel, Alcoa Labs, I visited in 1980. They had 1,200 people at this campus outside of Pittsburgh. Kennecott Copper had big labs in Lexington, Massachusetts. But almost all of that's gone. So if you want innovation, for example, in steel, where's it going to come from? If the remaining laboratories are reduced to basically firefighting for problems that are occurring in existing production facilities. The Bell Labs, yeah, Bell Labs is a fantastic place where people were able to roll. They didn't have to just work on improvements to the telephone system. Um, so what's left? Where are the innovation centers? That's going to be in the university. Um, and there have been many inventions that have come out of universities that have led to spinouts and then eventually new companies. Um, and so it's going to be driven by the nature of the funding, because if you take a look at the power of the American university system, the intellectual horsepower there, it's unmatched anywhere else in the world. But it pivots on the availability of funding. If the funding from the NSF, from the DOE, and so on becomes overly prescriptive, then you leave out the possibility of surprise. If everybody is told that they must work on long duration energy storage using flow batteries, don't be surprised that you don't see breakthroughs. So I say that the intellectual horsepower is there in the universities. And I just, with the cautionary comment that make sure that the funding doesn't come with too tightly positioned guardrails.
On that note, I mean, can you speak a bit about the difference, I guess, between translational and just general research? I mean, it sounds like you're saying that a lot of the breakthroughs and the innovations come from professors and inventors that are able to roam, whereas these prescriptive or sponsored research initiatives might even be too narrowing, which would probably fall more in the translational research category, correct?
Yeah, I think that's probably correct. But the labeling is a little bit unclear to me. I just think that the statement holds that you want to have, you know, I would like to urge people to go back to late 2009 when ARPA-E was funded. This is the Advanced Research Project Agency branch of the Department of Energy. And that was a golden moment because Stephen Chu was Secretary of Energy and had the authority to go ahead and establish ARPA-E, which actually was recommended under the previous administration when Sam Bogman was the Secretary of Energy. And they wanted to establish ARPA-E, but Congress wouldn't fund it. But then with the election of President Obama and the appointment of Stephen Chu, they got the funding. And I remember the first round. I was a first round ARPA-E winner myself. And the call was for bold, imaginative projects, the kind of which traditionally industry wouldn't fund, government wouldn't fund. And to the reviewers, the directions were, do not consider likelihood of success. Instead, consider potential impact if successful. And Arun Majumdar, who was the first director of ARPA-E, he came to MIT shortly thereafter and gave a presentation. And he said, of the 37 awards that we've made, he says the majority of them are going to fail, but the few that succeed will be game changers. Well, that's all gone now. Now it's likelihood of success is one of the factors, and so I would invite the administration to be a little bit less prescriptive and invite people to bring their wild ideas. Now, we're not going to fund science fiction. No perpetual motion machines need apply, but boy, let's look at how we can innovate by breaking inside the traditional barriers.
And so something that, first of all, that's really interesting to value impact over likelihood of succeeding. You talk a lot about how championing professors and their capability to invent the future, and you talk about inventing inventors. First of all, actually, before I get into that, do you feel connected to Professor Volta at all, the inventor of the battery? I mean, I know you mentioned him quite a lot. Is it just because you really focus on batteries, or is there something deeper there that you feel connected to him about?
Well, I think that the whole idea of doing something that's radically different. I mean, Volta, people think of Volta correctly as the inventor of the battery. What they fail to appreciate, and it's not their fault. I think that the science writers have failed to convey this, is that with Volta we get not only the battery, but we get the modern era with electricity, because prior to Volta, there was the term electricity. It was already used in the 1600s, but it meant static electricity. It meant what you could do with, if you took some amber and you rubbed it with some wool, and then you had a straw sitting on a beaker or containing in the water, and by moving the amber piece that had been rubbed, you could move the straw. And this was absolutely mysterious, because in the 1600s, the notion that you could move something without physical contact, in other words, action at a distance, this was magic. But that was the extent to which electricity existed. It was static electricity, and if you moved the object that had been charged, then you could, with that, move another object that was in close proximity. But with Volta, for the first time, we get electrons in motion. And within 10 years of the invention of the battery, people were applying electricity to actually conduct electroplating operations. And that all happened without venture mentoring or innovation hubs or any of that stuff. They just saw this thing and said, hey, we can do things with it. So I think that I have tremendous respect for Volta, because we're having this conversation thanks to electricity, and electrons in motion were first given to us by Volta. And then later on, there were some physicists that said, well, electrons in motion, they detected a magnetic field. And they said, wow, electrons in motion can generate a magnetic field. And then somebody else comes along and says, well, if I have a conductor just sitting there and I have a magnetic field in motion, can that generate electrons in motion? And that's the birth of the dynamo. And then, here we are. It all starts with Volta.
And you also talk about these 22-year-old young inventors that invented the aluminum smelting process, right?
Right.
So it seems like you really do see a lot of potential in these young scientists, and so you like to talk about inventing inventors. And if you have an idea, you then decide to, and it seems promising, you hire a student. I mean, can you talk about and I'd like to get more into the mentorship category of what you do, but maybe you could speak a little bit about how you invent inventors.
Well, I think it's by helping them unlock themselves. I mean, I don't use the vessel model of education where the student is an empty vessel and the professor has the water and pours the water and fills up the vessel, and the student leaves, having been filled with all of this knowledge. Because that's memorization of facts, and of course you have to know some things. You can't just say, well, I can look it up. You have to have a few things in near-term memory. But the whole business of inventing inventors is through the act of invention. So I take them along on a journey, and so we're working on, for example, in the TED Talk, there was the conversation about the liquid metal battery, and I have a team of about 20 people, postdocs, graduate students, and even some undergraduates. And just the whole operation of that, how I formulated the problem, how I got them to see the problem from my perspective, and then turn them loose, and encourage them, allow them to try things. They might fail, but what do we learn from the failure? Empowerment, building of self-assurance, self-confidence. These are all ingredients, and that's what I continue to keep with me. And out of that comes two things. You get the results of the research, and then you get the emergent professional. And finally, I guess the other thing is that I say that, okay, so we worked hard on this liquid metal battery, and we've got some patents now. We've got some research publications, some of them in the most prestigious journals on the planet. But you realize that in addition to the invention of liquid metal battery, that this exercise has been a metaphor. It's a metaphor for inventing. So I like to say that, if you go back to before World War II, an engineering education was just going through the past lessons. So that there would be these fat books, chemical engineer's handbook, mechanical engineer's handbook, electrical engineer's handbook, and the university professors were all professional engineers, and the students would just go from page one to the end of the book, and it was almost like learning to play a musical instrument. You get the writings of previous composers, and you learn to play them in ascending level of difficulty. And many people get to Carnegie Hall and perform, but it's not about the performance, it's about who's going to be the next writer. And so after World War II, the paradigm shifted so that now we teach people the fundamentals. So we learned from World War II that modern engineering is based in modern science. And so that means engineering education is now a science education, migrating towards applied science. And so I say that a good education teaches you to solve problems. A better education teaches you the methodology for solving problems. But I want to go beyond that. I want a great education which teaches you the methodology for developing methodologies.
And so, right, and you're teaching these people how to think and how to invent and how to come up with even the new methodologies for doing things. And so, if you had to think about some of the qualities that some of the best grad students or postdocs have, even the ones that rise to become the CTOs of some of the spinoffs that you've been involved in, I mean, what are some of those unifying characteristics that people should think about trying to hone and develop in themselves?
I think it's an irrepressible um, desire to accomplish something with a higher sense of purpose. I mean, the people that came to work on the liquid metal battery, uh, they wanted to change the world. And with that kind of passion and young idealism, all I got to do is just point them in the right direction and then turn them loose. They're going to be fine. You know, they're curious. I encourage them to be a little bit playful. Don't edit yourself. Blurt out the most ridiculous ideas, and we don't, shut anybody down. Um, and so those are all really good qualities.
And I like this idea of when you turn the student loose or students loose on the idea. I guess I'm interested to know how you know that an idea of yours is ready for a student to unleash, your army of students on that idea to go nuts. I mean, like, is there a feeling that you have, or how do you know when it's ready for that stage of the process?
Well, everything pivots on formulation of the question. So you start with there's a pressing need, an unmet need out there. So for example, grid level storage. If you go back to say 2005, people were talking about putting lithium-ion batteries in the grid, and I said this is stupid. It's far too costly, and it's not safe. So I started thinking, well, what's something that's going to be big and cheap and on and on and on. And eventually I came up with this idea for the predecessor to the liquid metal battery. And I just assessed it in terms of, if successful, would this thing make a difference? And I considered it would be. So now, who's going to do the work? We got to get people in the lab. We're going to try things. We've got to break this down into its constituent acts of research, and staff up, and away we go. So I knew from the beginning that I had an idea that was developed far enough along that I could foretell that if this thing pans out, it's going to be useful, it's going to be deployed. So how do I get from here to there? Students.
And how many of these ideas do you have that you're working on at any given time? And I guess I'm also curious, just in the process of you noodling on these ideas. I mean, is it stuff that comes to you in the shower because you've planted the seed properly, or do you set aside and allocate time to think about how to solve these large problems? Because it sounds like it takes years for you to come up with a potential solution that can then be worked by these armies of students. And so what's the process there, and how many of the ideas do you have, rattling around at any given time?
The process is to, just as you're going through your daily life, you encounter things that pique your interest, and you say, well, there's an unmet need here, and then in the meantime, there's also what I'm capable of. I mean, I don't touch the life sciences. It's Clint Eastwood playing Dirty Harry says in one of the episodes, a man's got to know his limitations, and so I don't touch the life sciences. I'm glad there are people out there who are working in life sciences, but it's not me. So I see the intersection of a plurality of major problems, many of them out of the sector of deep decarbonization, climate change mitigation, obviously energy, and the intersection of all of that and what I call extreme electrochemistry. So everything I look at, I say, is there an electrochemical response to this? Because if there is, I'm there. I'll work on it. And so with that as sort of the backdrop, I don't sit down and say, okay, from 10:30 to 11:15 today, I'm going to think about possible solutions. No, it could be in the shower. It could be riding from the Avanti Labs to back home on my Vespa motor scooter. I don't know where the idea is going to come from, but then when it does, then I document it and start saying, okay, but how do we bring this to reality?
And something that stood out for me in one of your lectures is this idea of using materials that are of the most common elements in the Earth's crust. Is that a place for people to start looking for solutions, or is that sort of a secondary thing that people should pay attention to when they're thinking about materials that would go into one of these solutions? Like, could somebody looking for a solution say, okay, here are the 15 elements that are the most common in the Earth's crust. Perhaps I can start trying to solve problems with these common materials. Maybe you could speak a bit about that.
Yeah, well, so for many of these problems that I'm attacking, they involve society, and so cost is a key factor. So I've coined the term cost-informed discovery. Now, the classical model of research at the university is invent the coolest chemistry, and get published in the most notable journals, build your career. And then if there is a possibility of a startup, spin it out and let the people there chase down the cost curve. And I say, but if you're talking about competing for something like energy storage against deeply entrenched, heavily subsidized fossil fuels, you can't do that. You got to start thinking about costs on day one, not day 1001. So how are you going to make something that is cost effective and better? You have to factor in, among other things, the materials of construction. And so that's why I say, if you want to make something dirt cheap, then make it out of dirt, and preferably dirt that's locally sourced. That way you have a secure supply chain. Well, it's one thing that the pandemic has taught us, is that globalization isn't all advantageous. There are some disadvantages to having key components of your most critical infrastructure arriving from halfway around the world. So in certain applications, I mean, if you're building something to a NASA price point, you can grab anything you want on a periodic table. But if you're building something that's going to have to go into a car, and you want that car to be competitive with the legacy automobile with the internal combustion engine, then yeah, you're going to be confined to a subset. I mean, I say if you want to invent something that's going to be widely applicable, and by the way, applicable in the developing world. I mean, you're not going to go into the developing world with first world solutions. So how are you going to do that? Well, you go in the backyard in the developing world, take a shovel full of dirt, put it on the lab bench, and tell your people, whatever solution you invent, the components have to come out of this pile of dirt. And that becomes your boundary conditions. And boy, you're going to start seeing people thinking the way they never thought before. So that's my take on subset of the periodic table.
And I really like that idea of things that researchers and grad students should be paying attention to as like on day one, not day 1001. Are there other things, apart from cost of materials, I guess, and cost of, production and manufacturing, are there other things that you think or you would advise young scientists and entrepreneurs to be paying attention to on day one as opposed to day 1001?
Yeah, there's been a big change, say in the last 10 years. Now people, you see it with respect to the pervasive lithium-ion battery. People are starting to ask tough questions about ethical sourcing. You've got cobalt oxide is one of the components of the lithium-ion battery. It's a key constituent of the positive electrode. And 2/3 of the world's cobalt comes from Congo. And there are some problems there with respect to mining of cobalt, exploitation of children, and so on and so forth. So people are asking questions about how is this sourced? And the second question people are asking is, what about end of life? What happens? Is this just going into landfill, or is it recyclable? Can it be reused? So that gets into not only the materials, but it goes to your other point about the manufacturing. It's one thing to make it, but can it be disassembled? Can it be reused? Or perhaps it can be repurposed. Maybe it doesn't come back as a battery. Maybe it comes back in some other form. But those questions are being asked. And so I'm working on a new battery right now. And one of the things that I've been mindful of is how does it stack up against lithium ion in terms of recyclability? So yeah, there are many more considerations that young people are being advised to take under consideration.
And so if you had to think about, how when a technology coming out of your lab is ready for spin-off or ready for prime time. I mean, I assume if you drill down, there are a few kind of micro stages within that, but how do you know when something is ready to be spun off, or when piece of research is good enough to start shifting it towards a commercialization effort as opposed to a research effort?
Once you've done enough research that you're confident that that the science is sound, and you know enough about what the say first generation product will look like, then it's time. And because you don't stay on campus and continue to do more and more research if you already know that you could build the first generation battery of this chemistry, but the question that remains is, will it scale? Because when you're doing the basic research, you just want to demonstrate that the fundamentals of the electrochemistry works. For example, that this thing will charge and discharge, and you get some performance parameters that allow you to think about how it would compare with the legacy battery technology. But you really don't know if it's going to work in a format that will power devices that are going to rely on this. So for that, you go off campus because you're going to be working at scale that is greater than what the campus can handle, and quite frankly, the nature of the work isn't the kind that would end up in a research publication or a thesis, and so it's probably inappropriate to be done on campus. So there's a push and a pull.
And are there other things, so thinking about production, thinking about, ethical supply, thinking about recycling and end of life, if we think about advising grad students and researchers on, well, let me say that it seems that people more and more in vogue are wanting to create new pieces of intellectual property and patent things and create startups. It's a bit different maybe, and maybe you can speak to this than it was in the last maybe 20 years, where people were more focused on publishing papers and just doing research. And so what are some other things that grad students and researchers should pay attention to if they are thinking about and shifting their attention to commercialization um, as a trajectory that they want to be on, patenting and things like that?
Well, I think it gets back to the asking the right questions. And when you pose the question correctly, that will give you a higher likelihood that you will approach uh, the trajectory to a solution in a successful manner. And the two are not at cross purposes. I mean, you can do really good fundamental work, end up publishing the archival literature, and derive something that is patentable, that can ultimately lead to the formation of a startup. So there's, I don't see these things as you choose one over another, one compromises the other. Yeah, there can be abuses in the system, but that's due to a failure of character. But people who have a higher sense of purpose and want to do something that will make a difference in the world, and say decarbonization, can be working on a technology and develop the IP and eventually go to a startup, and it's all correct.
And it seems like, so I think it seems like the majority of the work you've done has been at MIT, and the spin-offs that you've created have come out of your lab at MIT. Is there something that's unique to MIT that has fostered this within you and within your lab? And if you had to, what are some of the key elements that maybe we could even try to extrapolate to other universities and research institutions?
Um, well, that's a tough one, because in order for me to really answer it with correct background information, I would have had to have spent some time at other universities in a professorial role to be able to make the contrast comparison. But I'll just take a stab at it and say, MIT has been a place where there is first of all, there are very, very low boundaries. So, when I was at the University of Toronto, I was in the School of Engineering, I was in the Department of Metallurgy, and the notion that somebody would work with a colleague in the Department of Chemistry. The Department of Chemistry was in the School of Science, and but this is a different department, it's a different school, and there were sort of silos. People work within their own bounds and so on. I got to MIT, and people work with anybody. And this is going back to 1977 when I was there as a postdoc. So I hired on in '78, and so it was very, very fluid. So that many other things. Everybody had to teach, so there was no specialty of research faculty and so on. And I maintain that many of the ideas that I've developed are the result of the fact that I was teaching all the time, and as a teacher, I had to take ideas and break them down into their bite-sized pieces, so that the trajectory of the first-time learner would be correct. And in doing so, I had to challenge my own sort of take it for granted understanding as opposed to deep understanding. And plus the questions you would get from young people learning this for the first time, you would utter the whatever the pat explanation is, and then someone would ask you this question and just blow the explanation away, and you say, no, I guess that wasn't exactly correct. Let me get back to you on that. And so all of that, it's all working in concert to develop your mind. Um, and the students there are really very high functioning. Um, so those are all pieces of it. Um,
I love that
I,
idea of breaking things into bite-sized pieces. I mean, the best way to learn is to teach, right? And the fact that you're kind of reducing things to first principles is allowing and seeding your mind to come up with original ideas based on first principles, I think is really inspiring.
well, it's worked for me. I mean, I did not invent liquid metal battery by going to advanced uh, mathematical modeling that is now available to us thanks to the advances in computation. I invented the liquid metal battery with the principles that I used to teach first year general chemistry. And if you have a deep understanding of how elements react with each other, you can conceive of batteries. You don't need density functional theory to do that.
It's extremely inspiring. And so if we think about even the liquid metal battery and Ambri, or what is now Ambri, um, going back to MIT, it sounded like they had seed funds that paid for some of these prototypes, which, other research institutions have these, and I think MIT was probably an original leader in this. Can you talk about the importance of that and you know, or what it meant to developing the technology beyond the lab scale?
Yeah, so there was a fund that had been actually created by the generosity of a donor, Desh Deshpande, and I can't remember when he started that fund. It was in the early 2000s, and one of my the first student that worked on the liquid metal battery um, was supported by some seed funds from that center, and we got our first very very crude data based on experiments that were funded by this seed grant. And so at the time when I applied for the big grant from ARPA-E, I had those data in hand. And I believe that the liquid metal battery, as I presented it in that proposal to ARPA-E, was so radical that my fear is that it wouldn't have been funded were it not for the fact that we already had some early data. So there's no question that having this kind of, I like to call it mad money, that, we're talking about $50,000, $100,000. These are not princely sums, but without them, uh, you just don't have credibility on really far out ideas. So that was absolutely a critical component for liquid metal battery, and likewise on the molten oxide electrolysis. I had funding from the Deshpande Center in the early days of molten oxide electrolysis, and ultimately that led to Boston Metal and a really credible way to make steel without CO2 emissions. So this money is it's really critical.
And I'm glad you brought up molten oxide electrolysis. This company, Boston Metal. I mean, even they're a startup, and this was something you invented in like 2006, I think. So even like 15 years ago, potentially. Is that correct?
Actually, it's partly correct. I started working on molten oxide electrolysis in the late 80s. Yeah, it's been a long time. I really started, getting research funding probably in the 90s. Um, because this was related to extractive metallurgy, and in the late 80s, the federal government closed down the U.S. Bureau of Mines, so that was the natural home for research sponsorship of things that would pertain to extractive metallurgy. And so, metallurgy in those days was viewed as this is old stuff. The National Science Foundation wouldn't touch this. National Science Foundation, as the name implies, is science. There's no engineering foundation. Engineering has to, tuck in to the National Science Foundation. And in the area of material science, they were going after new materials, as they should. But the unintended consequence of chasing after carbon nanotubes and all sorts of new materials is that the old stuff is going to get marginalized or just shut out. And you could say, well, this is mature. But back to the beginning of our conversation about, by the late 80s, all of the industrial labs were pretty much decimated. So who's going to invent carbon-free steel making? If the National Science Foundation is going to sponsor research in this area, and the steel industry has lost its capabilities to innovate at the process level. And meanwhile, you've got this environmental imperative. If it weren't for the environmental imperative, we'd say we've optimized. We now make steel so well. Why do we have to innovate? And the answer is CO2 emissions. So, so I started back in the 90s, and I got a little bit of funding here and there for maybe 3 years, then no renewals. There was one moment there in the early 90s from the National Science Foundation. They're actually looking at some, I can't remember what the nature of the program was, but there was a contract monitor there who took an interest in what I was doing, and I got funded there, and then it went dormant. And then I got funding from NASA because NASA was interested in developing a technology that could generate oxygen on the moon using lunar resources. And so I morphed it in from molten oxide electrolysis to molten regolith electrolysis. Regolith is the dusty, powdery surface of the moon. It's basically soil, but it doesn't have any organic in it, so you don't call it soil. It's regolith. And so that got some funding. And then there was a moment in the early 2000s when the DOE, in partnership with the American Iron and Steel Institute, said, okay, well, we'll take a look at this thing, because they were really not keen to start looking at climate change mitigation technology. But I got funded on that piece by piece, and eventually got to the point where I was giving a talk. It was a Forrest Gump moment. I was giving a talk at a symposium in honor of a professor from the University of Cambridge, who I think it was his 70th birthday or something like this. And there was a person in the audience. He was a Brazilian who had made money in minerals. And he heard me talk about molten oxide electrolysis, and he approached me and he said, let's go for coffee. And coffee became dinner. And so what would it cost to commercialize this? I said, well, we'd start with $5 million and see what we can do with it over 5 years. And he said, okay, let's do it. So that's how the forerunner of Boston Metal started. It's around 2012, something like that. So it's a long journey.
Yeah, no kidding. And do you get grants? I mean, I know any good researcher is mostly also a pro in getting grants. Do a lot of these, do they come from the TTO? I mean, I'd like to hear about your relationship with the tech transfer, or the TLO, I think it's called at MIT. But also maybe you could touch on, how you are so effective at winning grants. I mean, do you have any idea what percentage you apply to that you don't win? Or I'd love to hear about that in any way.
Everything depends on the instant circumstances. I mean, I was, I think some of it is just luck, because the success rate in the physical sciences and engineering is really low compared to life sciences. I remember reading, I don't know, 4 or 5 years ago, something in the New York Times, somebody was saying, yeah, it's getting really tough in the life sciences. And I mean, fewer than 1 in 3 proposals is funded. I said, 1 in 3? So to give you an example, for the first round ARPA-E, there were 3,700 white papers, and of those 350, less than 10% were invited to submit full proposals, and there were 37 awards. Well, by my math, 37 over 3,700, that's 1%, 1% success rate. And by the way, no renewals were allowed. So, that's another interesting piece. Let's say the award is for 3 years. Well, these days it's taking 4.5, 5.5 years to get a PhD. So you imagine a student is 3 years into his or her PhD and the professor doesn't get renewed. Now what? So it's brinksmanship all the time. It's brinksmanship.
And so you're constantly on the lookout for new sources of funding.
That's correct.
And okay, and so I assume, I guess that takes probably quite a bit of your time. Does the TTO help in any way, or they don't really touch this funding thing? They're mostly on the commercialization and sponsored research side of things.
That's correct. The Technology Licensing Office handles the application for patents and the licensing of technology. They do not fund research.
No, but I mean to say, like, do they help facilitate sponsored research in any way from industry?
No, they're really focused on getting the technology out of the file cabinet and into practice, because they have a fiduciary responsibility to the university. They want to turn technology into a revenue stream. So the revenue stream will then go to the university, and then maybe there's some tortuous path by which some of that ends up in some on-campus seed funding, but it would fund more likely the infrastructure of the university, because the sum of tuition and overhead doesn't pay for the full cost of running the university. So by having a rich revenue stream coming from the inventions of the students and the faculty, that helps keep the university running. But there isn't a direct line of sight from the TLO and sponsorship. And people, let's say corporate entities that are going to the TLO, they're not going to the TLO to say, hey, what's going on at the university? We'd like to sponsor something. No, they're going to the TLO because they're saying, we're looking for new technology in such and such a sector.
So yeah, I mean, I asked just because I'm interested in the mechanics of all of this. There is no systemized way for or any kind of platform or marketplace or anything like that for facilitating sponsored research between what's going on in your lab and any industry that might be interested in doing, in sponsoring it.
Well, actually, there is the Industrial Liaison Program, which was founded probably around 1950. It was the first of its kind, And so the industrial liaison program has a staff of people that make it their business to know what the faculty are doing. They're divided, the staff are divided by field of knowledge. And so there are people at the ILP who make it their business to be familiar with current research that's going on. And the faculty know that the ILP exists, so we would communicate with our ILP staff member so that he or she knows what we're doing. And then on the flip side, companies from all over the world choose to become members of the ILP. And so, and then not just in the United States, people from all over the world. And so let's say I'm a metals company, and I'm interested in alloy development. So I could, granted, we have this thing called the internet, the World Wide Web, and so on. But to be quite honest, people in the research arena aren't necessarily going to put their absolutely hottest, most recent ideas on display. So you could find out who's working on alloy development, for example, but you're not going to find out what the latest idea is that person is working on. But through the ILP, you can get introduced and then have meetings and so on. And by connections through the ILP, I've enjoyed industrial sponsorship on numerous occasions, and it works both ways, because through the industrial sponsorship, I got to visit the companies, because if I happen to be in Europe and I'm going to be in France, so I can go and visit the big French metals company and actually give a talk at their headquarters, but then go to one of their smelters. And, I was in the foothills of the Pyrenees visiting a magnesium smelter that uses a technology totally different from what is used in the United States. There's no way I could have gotten in there as a young assistant professor, but for the fact that I was introduced through the MIT Industrial Liaison Program. So, and that not only cultivates the research, but it informs me now when I'm teaching. I mean, can you imagine being taught metallurgy by a professor who's never been to a smelter? Everything the professor knows, he or she got by reading books. Well, that's fine. That's fine. But, to say, I was there. I visited Béchinet in Marignac. I know what this process looks like. I visited Reynolds in Muscle Shoals, Alabama. So it's you speak with having been there.
I love that. And so I want to be respectful of your time. I have a few more questions I'll try to get in within the next few minutes. Do you ever have any designs on leading one of these spinoffs? I know you're sitting at the Avanti headquarters right now, or do you ever think about becoming the CTO or CEO of these initiatives?
No, because I've got too many other ideas. So I want to get them out the door, launch them, empower the people, and then get on to the next idea. It's if I were out of ideas, then I would say, all right, I'm going to ride this one. But I'm not. I got other ideas.
It hasn't happened yet.
I can't wait to get Avanti on its way, because I've got there's some others.
And how do you? Yeah. Oh, sorry. Go ahead.
No, go ahead.
No. I appreciate. I keep saying what you were going to say about other ideas.
I have other ideas. I was going to tell you what they are, but I decided no. I'm not going to.
Okay. All right. Yes, this is a publicly available podcast. Maybe later we'll do another episode and we can talk about future ideas. And how do you know when to step away from Avanti?
When it's properly funded, it's properly resourced. when it's properly resourced. That means it has the money to go on its route, and it's got the staff. And when I see I've got surrogates that are perfectly capable, I mean, I'm still around, and they can pay me for, you know, scientific advice or stuff like that. But I have the humility to know that I can do things in the technical arena, but I don't fancy myself as a business strategist. So, you know, as I said before, a man's got to know his limitations, and so I play to my strengths and don't get in the way.
And if you had to think about advice that you would give to young grad students, scientists, postdocs, researchers, entrepreneurs that are looking to do meaningful work and, you know, fix this environmental imperative, what would you say to them? Give me about anything.
I'd say just get technically literate, and then dive in. Choose the problems that inspire you, that you feel passionate about solving, and you know, harness the intellectual horsepower of your brain, and get on the journey.
And what would you tell the young Donald what would you tell yourself, the young Donald Sadoway, when you were leaving your PhD or in your postdoc, just at the beginning of your kind of career trajectory? What would you do differently? What would you tell yourself? Anything on that?
Well, if I knew then what I know now, it would have been a meteoric trajectory. But I think it was, if I had something to do over again, it would be to follow my instincts and grant myself permission to be audacious and take on big problems. But in the early days, I was really a really good boy who always painted within the lines, did everything correctly, so as to make sure that I achieved tenure and so on. But I think, you know, being willing to take risks, and that means intellectual risks. It would have been, that would have accelerated the progress. But otherwise, I was really lucky that I followed people. I became an electrochemist because there was somebody at the University of Toronto in the metallurgy department. This person, I said, I like this person. I mean, I want him as a friend or anything like that, but I like the way he thinks, and I like the way he conducts himself. So it was both his character and the way his mind worked. He taught thermodynamics, but his research was in high temperature, non-aqueous electrochemistry. If he'd been a ceramist, I probably would have been a ceramist today, but he was an electrochemist. And that was my good fortune. And then I chose to come to MIT and postdoc with somebody else who was, again, I chose the person. And by choosing the people and learning so much from them, both in the way they went about it. The person at MIT was Julian Zakelli. He was involved in transport phenomena, but he was this is 1970s. He was being quoted in the press about the connection between the science and the economy and so on. And so I saw the societal involvement, and those are formative experiences that helped move me along. So you know, don't work on something because you think it's in vogue, but you really don't like it. But you've heard that Graphene is really hot right now, but you really don't like graphene. It doesn't really excite you. So what are you doing that for? Just work on something that excites you.
Well, that's good advice. Work on something that excites you, follow good people. I'm sure there's a bunch of great people that followed you, or it's obvious that we can see. And so I think it's a great place to end. Professor Donald Sadoway, thank you. Is there a place where people can find you that you prefer? LinkedIn, Twitter, anything like that? Or your website, I guess, as well?
All the above. You can find me LinkedIn, you can find me Twitter. You can find me at MIT. You can get my email address. It's no secret. So just reach out.
Excellent. Professor Donald Sadoway, thank you very much for joining us. Everyone visit bountiful.work to get early access to our platform. Thanks again, Professor, for joining us. I really appreciate it.
My pleasure. Good luck.
Thanks for listening. But now we need your help. We're building a community of scientists, students, entrepreneurs, industry leaders, and investors to commercialize meaningful technology and research. Join us at bountiful.work today to find opportunities and realize your power to save the world.